Constructing a quadratic polynomial from its zeros. Hello everyone. Welcome to today's lesson. Before we dive into our new topic, let's take a moment to reflect on what we have already covered. In our previous sections, we focused on how to find the zeros of a quadratic polynomial and explored the specific relationships between those zeros and the coefficients of the polynomial. Now, today, we are going to do something a little different. In this subsection, we are going to reverse that entire process. Instead of starting with a polynomial and searching for its zeros, we will learn how to work backwards. We will learn the method to construct a complete quadratic polynomial from scratch, provided that you are already given its zeros, or perhaps just the sum and the product of those zeros. Let's get started. Understanding the concept. Suppose we already know the zeros of our quadratic polynomial, and we'll call them alpha and beta. If we have these two values, we can actually express the entire polynomial using just these zeros. To understand how, let's look back at the standard form we are all familiar with, where p of x equals a x squared plus bx plus c. In our previous lessons, we studied the vital relationship between these coefficients and the zeros. Specifically, we know that the sum of the zeros, alpha plus beta, is equal to negative b over a, and we also know that the product of the zeros, alpha times beta, is equal to c over a. Now, here is the clever part. If we take that general form, a x squared plus bx plus c, and divide the entire expression by the coefficient, a, we can rewrite it as a multiplied by the quantity x squared plus b over a x plus c over a. Now, look closely at what happens when we substitute those relationships we just mentioned. Since negative b over a is the same as the sum of the zeros, then b over a is actually negative of the sum of the zeros. And since c over a is the product of the zeros, we can rewrite our polynomial as a multiplied by the quantity x squared minus the quantity alpha plus beta x plus alpha times beta. To make this formula even more versatile and general, we often replace the coefficient, a, with a real constant, which we call k. This gives us our master formula, p of x equals k, multiplied by the quantity x squared minus the sum of the zeros, x, plus the product of the zeros. Keep this formula in mind, because in the next slide, I will show you exactly how to use it step by step. Now that we've established that we are reversing our previous approach, let's dive into the core concept of how this works. Step-by-step procedure to construct the polynomial. Now that we have understood the mathematical theory behind the relationship between zeros and coefficients from the previous slide, let's break this down into a practical, step-by-step procedure. If you follow these 4 manageable steps, you will be able to construct any quadratic polynomial with ease. Step 1, your first task is to find the sum of zeros. Simply take the given zeros, which we call alpha and beta, and calculate their sum, alpha plus beta. Step 2, next, you need to find the product of zeros. This involves multiplying the two zeros together, which we represent as alpha times beta. Step 3, once you have these two values, you will substitute them into our general formula. You'll plug the sum and the product into the expression, k multiplied by the quantity x squared minus the quantity alpha plus beta times x plus alpha times beta. Step 4, finally, you must simplify the expression. This means cleaning up any double negatives and simplifying the coefficients to arrive at your final polynomial. Now, a quick tip. Unless the problem provides a specific point that the polynomial must pass through, we usually choose k to be equal to 1 to keep the polynomial in its simplest form. In the next few slides, we are going to walk through some concrete examples to see this exact process in action. Illustrative examples. Now that we have understood the theory and the general formula, let's put it into practice with our first illustrative example. This particular case is a bit simpler than the next one we will see, because here, the sum and the product are directly provided to us. Take a look at the problem statement. We need to find a quadratic polynomial where the sum of the zeros is 1/4 and the product of the zeros is -1. To solve this, we start by identifying our given values. We have the sum of zeros, alpha plus beta, equal to 1/4, and the product of zeros, alpha times beta, equal to -1. Now we will substitute these values into the general formula we derived in the previous slide. The formula is p of x equals k times the quantity x squared minus the sum of zeros times x plus the product of zeros. Plugging in our values, we get p of x equals k times the quantity x squared minus 1/4 x plus -1. To make it look a bit cleaner, we can rewrite that plus -1 as simply -1. So we have p of x equals k times the quantity x squared minus 1/4 x minus 1. At this stage, you might notice a fraction in our expression. While this is mathematically correct, we usually prefer a polynomial with integer coefficients. To clear that fraction, we can choose a value for our constant k. If we choose k equals 4, we multiply every term inside the parentheses by 4. This gives us p of x equals 4 times the quantity x squared minus 1/4 x minus 1. When we distribute the 4 times x squared becomes 4x squared. 4 times -1/4 x becomes -x, and 4 times -1 becomes -4. Therefore, our final answer is, the required polynomial is 4x squared minus x minus 4. This is a much cleaner version of the same polynomial, and it's exactly what we're looking for. Illustrative examples continued. Now that we've seen how to handle cases where the sum and product are given directly, let's look at our second example, which is slightly different. In this case, we aren't given the sum or product. Instead, we are given the individual zeros themselves. The problem asks us to find a quadratic polynomial where the zeros are 3 and -5. To solve this, we'll follow the step-by-step procedure we discussed in the previous slide. First, we need to calculate the sum of the zeros. We'll let alpha be 3 and beta be -5. When we add 3 and -5 together, we get a sum of -2. Next, we need to find the product of these zeros. We multiply 3 by -5, which gives us -15. Now we move to the substitution step. We take our general formula, remember, the one involving the constant k, and plug in our values. We write p of x equals k times the quantity x squared minus the sum of the zeros times x plus the product of the zeros. Substituting our values, we get p of x equals k times the quantity x squared minus -2x plus -15. Now, pay close attention to the signs here, as I mentioned in our common mistakes slide coming up. Since we are subtracting a -2, that middle term becomes +2x, so our expression simplifies to p of x equals k times the quantity x squared plus 2x minus 15. To find the simplest form, we can choose k to be 1. This leaves us with our final polynomial, p of x equals x squared plus 2x minus 15. So, our final answer is that the required polynomial is x squared plus 2x minus 15. Real-world analogy. Imagine, for a moment, that you are an architect tasked with designing a beautiful parabolic arch for a new bridge. In this scenario, you aren't just working with numbers on a page, you are working with physical structures. You already know exactly where the two ends of the arch must meet the ground to support the bridge's weight. In mathematical terms, these two specific points where the arch touches the ground are your zeros, or what we call the x-intercepts. By identifying these two fixed points, you can use the construction formula we just practiced, the one involving the sum and product of the zeros, to determine the exact mathematical equation of the curve. This equation tells you precisely how the arch should bend, ensuring the bridge is both structurally sound and mathematically perfect. Now, before we move on to some important tips on avoiding common errors, let's take a moment to step away from the abstract algebra and look at how this concept actually applies to the real world. It's a great way to see that the zeros we've been calculating are actually the foundation of the entire shape. Common mistakes to avoid. First, watch out for the sign error in the sum. This is perhaps the most frequent mistake students make. When you look at our general formula, remember that there is a negative sign placed right before the sum of the zeros. Specifically, in the expression x squared minus the quantity alpha plus beta times x, that minus sign is crucial. If your calculated sum, alpha plus beta, happens to be a negative number, that double negative will turn the term positive. For example, if your sum is -2, then minus -2x becomes plus 2x. Always double-check your signs here. Second, be careful not to confuse the sum and the product. It is easy to accidentally swap them during substitution. Just remember, the sum of the zeros, after you've applied that sign change, must always be the coefficient of the x term, while the product of the zeros should be your constant term at the end of the polynomial. Finally, do not ignore the constant. K in the examples we worked through earlier, like in example 1, we chose a value for k to clear out fractions. While it is very common to simply assume k equals 1 for the simplest form, keep in mind that there are actually infinitely many polynomials that share the exact same zeros. They are all simply multiples of each other. Now, before we wrap up our lesson, I want to pause and discuss some common pitfalls. Even if you understand the formula, it is very easy to make small errors that lead to the wrong final answer. Let's look at some common mistakes to avoid. By keeping these 3 points in mind, you will be much more confident in your calculations. Now, let's move to our final slide to summarize everything we have learned today. Key takeaways. First and foremost, remember the master formula we've been working with. To construct any quadratic polynomial, you can use the general formula. P of x equals k multiplied by the quantity x squared minus the sum of the zeros times x plus the product of the zeros. To make sure you don't get lost in the symbols, just remember that alpha plus beta represents the sum of the zeros, and alpha times beta represents the product of the zeros. Lastly, don't forget about that constant, k. As we discussed in our examples, k acts as a scaling factor. While changing the value of k will change how steep or wide the parabola appears on a graph, it will not change the positions of the zeros themselves. The points where the curve touches the x-axis remain exactly the same. All right, we have reached the end of our lesson, so let's wrap everything up by reviewing the key takeaways from today's session. I hope this summary helps solidify your understanding. Keep practicing these steps, and you'll be able to construct these polynomials with ease.